Okay, well, good afternoon, everybody, and welcome to the launch event of the Center for Post-EPR Spectroscopy here at Imperial College London, PEPR. Welcome here in person and online, of course. It's great to have you and to be able to do this hybrid event in these times. My name is Maxie Roessler, and I'm the director of PEPR, and it's my great pleasure to introduce our first speaker, Professor Richard Craster, who is the Dean of the Faculty of Natural Sciences and Professor of Applied Mathematics. And thank you very much for coming here to open our launch event.
Thank you very much, Maxie. What a pleasure it is to stand here in person in a lecture theatre and say a few words. And welcome to the launch of PEPR. PEPR is a unique centre situated at the heart of Imperial's White City Research and Innovation campus, based in the new MSRH building. It's not quite perfectly new, but almost new. It's very, very recent. The MSRH is a visible demonstration of the commitment of Imperial College to the advancement of fundamental and translational science. PEPR aligns very strongly with our vision to bring scientists in academia and industry together. And I was struck by the range of partners. Maxie very kindly gave me the proposal to read through, so I dutifully read it through, and what a wonderful proposal it was too. By the range of partners, including over 13 CDTs, national, international and university partners, and of course industry playing a key role. In fact, there were more than 70 partners listed, and then of course there are SMEs, which are based in many of whom are based in our Translation and Innovation Hub right next door. The connections to our strategy were striking, and also to the underpinning of our national strategy as we emerge from this crisis in giving us a facility with national capability. I'd like to thank Brooker in particular and the EPSRC for their role in making this happen. And now I'm going to hand back to Maxie. And welcome, of course.
Well, thank you very much, Richard, for the kind introductory words. So it is now my pleasure to tell you a little bit about the vision of the Center for Post-EPR, or PEPR. So I like to think of PEPR as being built on these three pillars. So state-of-the-art multi-frequency, post-EPR, electrochemical EPR, and instrument development. And I think all these really come together to help us fulfill our three main aims. And the first of these is really to explore the power of electron spins across different disciplines. And EPR spectroscopy, so electron paramagnetic resonance or electron spin resonance, of course looks at unpaired electrons, not necessarily in the ground state. You'll also hear about them in the excited state here. And I think it's really a discipline that really spans all the way from biology to physics and everything in between. And here it's just one selection of work packages that we had for the grant here, where we felt we had a particular strength and some particularly compelling projects that EPR would contribute to. But it's not just about electron spins across different disciplines, it's also across sectors. And I think this is an opportunity brought to us here where we are on the new White City campus, where we are and where we are right now. And it's really an exciting co-location, I think, of academia, industry, and even the local community. And I think you'll hear more about that from Oscar says at the end of the day. And secondly, what we want to do is to bring some new capabilities to the field of EPR spectroscopy. First of all, this is in terms of spin sensitivity, so spin concentration and spin number. And that's a topic that's particularly close to my heart. My own research mainly falls into this work package here, protein function, where we often have to work very hard to get these unpaired electrons in sufficient concentrations to do something interesting with them with post-EPR. So I think this is really game-changing. And the second aspect here is some method developments that we are doing here to be able to study processes that are underpinned by oxidation and reduction. So effectively watching radicals evolve during these redox reactions. And the third point, not last but definitely not least, is really to satisfy what I think is quite a high local and regional demand for post-EPR and for multi-frequency EPR. And as Richard already alluded to, we had some 70 or so academic groups and SMEs and so forth interested when we submitted the proposal, which is really fantastic. Now let me introduce the team to you, the PEPR team, so all my co-investigators who made it all happen, of course, with me. So first of all, Sandrine Heutz here from Materials, and Bill Rutherford from Life Sciences, and Ashley from Chemistry. You can see I've sort of categorized them into the three pillars, but of course that's definitely not mutually exclusive. They do all come together in many ways. John Morton here at UCL is leading on the instrument development aspect, myself on the electrochemical EPR, but very much supported here by Anthony Kucernak, who's an expert in the electrochemistry side of things. And we're also very lucky to have a fantastic external advisory board consisting of Dave Britt at UC Davis, Eric McInnes from Manchester, Enrica Bordignon at Geneva, and Chris Wallace from Polymateria, who's representing the SMEs. And I'm very happy to say that all of them agreed to speak today. So hopefully by the end of the day, you would have seen a showcasing of what electron spins can do for you, and really a great range of different subjects and different disciplines. So I thought I'd take the opportunity to tell you about a couple of projects very briefly that I've been involved in, that have sort of already been affiliated with PEPR in the past year. The first one here relates to sensitivity that I already mentioned. So this you will hear more about from John Morton later on today, using cryogenic preamplifiers to effectively increase the signal to noise by more than an order of magnitude. And what we've used this for is to look at a single proton talking to a single unpaired electron in this enormous enzyme, respiratory complex 1. And what you see here is a two-dimensional technique that we've employed HiScore to look at that proton coupling, and that's the spectrum after just 1 hour compared to the conventional setup in the same amount of time, where clearly that would be completely uninterpretable. So let me just emphasize that these cryogenic preamplifiers, they are in principle widely applicable to all pulsed EPR techniques, and indeed we made further use of that to look at an enzyme that is even more challenging to obtain in large quantities. So we had very small and dilute samples to work with to investigate photosynthetic complex 1, for which the mechanism was not really understood at this point, and our contribution was to look at electron transfer using double electron resonance spectroscopy, and also making use of the cryogenic preamplifiers, and that's quite hot off the press, as to say, just published last week. So when I introduced the PEPR team to you, there's a key person missing here, and that's Alberto Collauto, who joined us in March as the PEPR facility manager. And he really has expertise in many different areas, using EPR across material science, proteins, high field pulse EPR here in this first postdoc, then moving on to more protein work, but also EPR methodology in Frankfurt. And I think now he's really in the possession to bring all of this expertise together in his current role and to support these three pillars of PEPR perfectly. And some of you will have had the chance to go on some tours with Alberto today. If you haven't and we haven't been able to accommodate you, then I apologize, and hopefully you'll have the opportunity soon, and please do get in touch and we'll be very happy to show you around. Now, in terms of accessing the facility, I guess the first thing to say is please do get in touch with us. We're very happy to talk to you. We also have a form online now on our website, which is really meant to be very quick and easy for you to fill out. It's really just so that we get a bit of a feel of what you want to achieve scientifically, and that we can best think what sort of EPR experiments would be most suitable to support that. And of course, I also invite you to join our mailing list, which you can also do via the website, and perhaps to consider following us on Twitter if you're not doing that already. I should also put a little disclaimer here that the website is still work in progress, so please bear with us while we perfect that, such as information on sample preparation and so forth. But for those of you joining us online today, we do now have a virtual tour of the facility, so I invite you to perhaps have a look at this link here on the website. So that brings me, I guess, to coming back to our vision here for PEPR. So first of all, to explore electron spins across disciplines and sectors. Secondly, to bring new capabilities to EPR and to satisfy demand. But let me perhaps also spell out the obvious. The ultimate output for us, I think, is to bring people together to do great science, to translate that knowledge, and to hopefully make an impact in society. So with that, I'd just like to thank everyone here who's been involved, and that's first of all the co-investigators and all the supporters of PEPR. Too long a list to all put up here, but clearly without you, we just wouldn't be here today, so I'm incredibly grateful to you all. I would also like to thank our funder and our industrial partnerships, so the EPSRC for funding this project, and you will hear from Daniel Smith just after me. And I'm also very grateful to Brücke for being very supportive with this project, and was also funding part of the reception this afternoon, as is Cryogenic, who's much more local, 2 miles from here, so in Acton, and who's working with us on making our facility future-proof in terms of cryogen-free technology. And you'll hear more about that from Jeremy Good. And on the Imperial side, again, there's many people to thank, but nonetheless, I do want to single out a few people. First of all, that's Alberto, who has simply, I think, made heroic efforts since joining us in March. But also my two postdocs, Mariam and Jana, who've taken on a huge amount of the groundwork before Alberto joined us, also in terms of infrastructure. None of that was in the job description, of course, and very much supported by Tim Jefferson and the whole technical team. I'd also like to thank the rest of my group for helping out today in the launch event, and of course generally in being so supportive with this endeavor to build up post-EPR here. I'd also like to thank Sarah, who's always very modestly in the background, but who's been incredibly supportive in putting the logistics of the grant together and helping with today's launch event. Also Erica, our departmental operations manager, and Oscar Says, right at the back there, our head of department, last but not least, for giving really some invaluable advice along the way. So with that, thank you very much for listening. That's all from me, and I'd like to hand over online now to Dr. Daniel Smith, who is head of physical sciences from the EPSRC, and I'm really delighted that he's able to join us online today.
Hi there, I believe I'm now live, so I'm hoping that everyone can hear me. I've got the lecture theatre at the front, so I can't see anyone in the audience, so I'm assuming that everyone can hear me. Apologies, I can't be with you in person today. I do look forward to getting across to White City campus as soon as possible, and certainly a visit is on the card. As Maxie said, I am head of physical sciences at EPSRC, which is part of UK Research and Innovation, and I'm just going to bring up my slides. So I'm assuming that you can see my slides on the main screen. Okay, so yeah, as I mentioned, Daniel Smith, part of the Engineering and Physical Sciences Research Council, part of UK Research and Innovation. And my responsibilities is for the health of physical sciences in the UK, covering antimatter through to chemical biology and everything in between. We make investments in state-of-the-art research, infrastructure, and also supporting skills across that spectrum. So for those who don't know, UK Research and Innovation is the main funding agency in the UK for research and innovation. We were formed in 2018, and we bring together 9 organisations with great depth and breadth of expertise that allow us to research communities, institutions and businesses and wider society in the UK and around the world. This combination allows us to work across the whole R&I system, informed by our networks and expertise. As the slide mentions, we invest £7 billion in research infrastructure and skills, from understanding the fabric of the universe to working with school-aged children to drive citizen science projects addressing climate change. Our remit is vast and vibrant. So within this gives great responsibility in terms of our vision, and which is about delivering an outstanding R&I system in the UK that gives everyone an opportunity to contribute and to benefit, enriching lives nationally, locally and internationally. As the UK's largest public funder in research and innovation, it's a responsibility to ensure the health of the system as a whole, now and into the future. So to do this, we're working across our partners to shape a dynamic and diverse and inclusive system that is an integral part of society that gives everyone an opportunity to participate and benefit. To do this, of course, we have to build on our mission, which is about convening, catalysing and investing in close partnership with our community and stakeholders. And that's why events like today and hearing about the science in this afternoon is really quite important in terms of helping shape the future strategy, both locally within physical sciences and beyond. If we take a lens down into the Engineering and Physical Sciences Research Council, our vision for beyond 21-22 is based around our 6 priorities that we've set out here. And these priorities are about driving world-leading engineering and physical sciences research. Across our investments, we'll set the foundations for resilient and sustainable prosperity for the UK. And to do this, we'll invest in discovery, mission-inspired and translational research that addresses the UK's needs now and also into the future. These priorities, which you can see on the screen, are science-focused, which are required to reinvigorate the engineering and physical sciences research pipeline. They'll be balanced to ensure a diverse research community that is mobilised to address major economic and societal challenges, and also address and understand curiosity-driven questions within our research disciplines. They'll be outcomes-driven to ensure scientific discovery leads both in the short and the long term. But the most important part here, of course, is ensuring that engineering and physical sciences can play an important role in the future in a post-pandemic world. But underpinning all of this, and the main reason why we're here today, of course, is that the UK's world-leading innovation strategy, research and innovation status, is predicated on well-founded labs, access to world-class infrastructure, and international facilities, which UKRI has an important role in both sustaining and investing in the future capabilities. We know that these facilities, as colleagues across in the room, assuming there's in the lecture theatre, we know that this attracts international talent, users, and it contributes to local and international strategies that enable us to add productivity and also the creation of new knowledge. So in recognising this, in 2019 and 20, colleagues from across UKRI conducted a review that looked at our infrastructure landscape. As UKRI alone, we support over 500 infrastructures from national supercomputing capabilities to museum collections. And these are inherently multidisciplinary and work across the stakeholder landscape. Importantly, as you heard from Maxie there, we support through these infrastructures a significant number of staff who are highly skilled and are key to the success of these infrastructures. This report, both the landscape analysis and the future capability, identifies potential opportunities to create a step change in the next generation infrastructure that will allow the UK to be a global leader in research and innovation. These reports don't set out hard recommendations, but set out a framework to guide decision making and identification of priorities through to 2030. Through these recommendations of the report, we now have a pan-UKRI-wide activity that is looking to identify and prioritising the step changes in infrastructure capabilities and capability that will deliver that overall vision and aspiration. This is also in addition to our local council strategies, which remain vitally important in this landscape. So within UKRI, my colleagues in the research infrastructure team provide the funding for equipment through multiple different routes. And this is about enabling researchers to access the equipment that they need to deliver the outcomes for their research in the most efficient and effective way. The scale of uses range from single to user to national facilities, supporting specific project activities all the way through to international collaboration. Investments in our equipment span from maintaining capability and competitiveness through to the creation of new state-of-the-art capability that allows for transformative cutting-edge research and innovation. Looking closely at PEPR and the facilities we're talking about here today, your strategic equipment is intended to enhance UK scientific capability and support a high quality cutting edge research across the remit of EPSC and beyond. Going beyond, EPSC is focused on continuing to build in these capabilities, but also looking to understand our future needs such that we can work in partnership with the community to invest in infrastructure where it's needed the most. But in addition to this, we're also looking at the support and recognition for research technical professionals. What is our role within that? How can we work across the landscape to enhance the career pathways there? Within net zero, we're considering how can our research infrastructure investments contribute towards environmental sustainability? What's the role of setting frameworks and standards and best practice there? And of course, as we heard from Maxie, the importance of our research infrastructure in levelling up and wider growth. But a topic that, of course, we've just heard about in terms of enabling connectivity and working across the stakeholder base is that enhancing capability across the research infrastructures, both from the institutional capabilities through better sharing and access and building on different initiatives like a virtual tour of facilities so people can understand the capabilities and what they can receive through working with state-of-the-art infrastructure like PEPR. But looking across the UKRI capital landscape, we've invested £7.5 billion So this pan-UKRI report recognised there is a significant role for UKRI in building better connectivity and enhancing the connectivity between our research infrastructures. So this recognises that there is a significant role to continue to both invest in the infrastructures, but also maximise the investments that we've made to date, such that the research community can benefit. So our aim here is to build a more connected landscape and enhance our connectivity through partnership working across all scales. So looking at our facility that we're launching today, clearly the capability has the foundations for transformative insights. It builds on many of the strategy areas that we're developing across UKRI. It builds on distributed EPR capability across the UK, and the unique facilities and capabilities based at the White City campus will allow us to build on new material insights into a range of underpinning research areas that are both within the EPSC remit and beyond, which is a great asset that we must build on. So I guess there's a lot of exciting things that can be enabled through the research. I'm looking forward to hearing from the presentations this afternoon, but also to looking to working with yourselves and with other transformative capabilities across the UK to find out how we're enabling discovery across our remit, but also how we can play a role in enhancing careers of research technical professionals, and also how we can maximise our facilities going forward. So I look forward to hearing the presentations this afternoon. Thank you.
Thank you very much, Daniel, for joining us online here and for continuing to be present in this virtual space with us today. So I'd now like to hand over to Dr. Jeremy Good, who's the director at Cryogenics Limited, who's been pioneering cryogen-free technologies and methodologies. And
so how do I advance the slides? Right. Good. Right.
Go. Okay. Yeah, so just
right.
Perfect, yeah.
Okay, so first thing to say is that liquid helium is a finite resource. It doesn't stay in the atmosphere, it escapes into outer space. And we get it from natural gas wells. Now, quite what's going to happen when we don't produce natural gas for reasons of global warming is not clear. And so it's a thought, it all comes from alpha particles in the depths of the Earth, which are trapped along with gas. And at the moment, some gas wells have up to 1% of helium in them, but it's extracted when you liquefy natural gas for transport. And over the last few years, it's increased enormously in cost, from around £2 a litre to 13 or 14 pounds a litre. And if you're running an experiment that requires a litre an hour for a whole year, you're looking at a very large bill, well over £100,000. But there has been some improvement, because over the last 20 to 25 years, we have got now cooling machines, which are mechanical refrigerators, and it's interesting that it's not a picture of a GM, but however, it looks very similar. It has a moving piston, and it extracts heat. You get about 1 watt of cooling power, or 1.5 watts of cooling power at 4.2 K. It drops to 2.5 Kelvin, there's no cooling power. You get more, slightly higher temperatures from the second stage, which is the bottom of these two copper. I don't know this, yes, things, whether you see that. All right, yes, that's the lower temperature, and that's the higher temperature device. So, there are two types. One is the mechanical one, and then this should be in a pulse tube, but they've been reversed in this slide, which I just noticed. And they're driven from a compressor. So you have compressed helium gas, which goes into the machine, is expanded in it, and provides the cooling. However, it's important to think that you get 1 watt of cooling power at 4K, but you need 7.5 kilowatts of 3-phase mains power to provide that 1 watt. So it's quite expensive to do, and these days the price of electricity very high, between 15 and 25 pence a kilowatt hour. You're still looking at a couple of pounds an hour. So you want to look after this cooling power very carefully. And so in order to cool a system, we produce, this is the cryostat we use for EPR. The sample is inserted through the top. There's a little window there that goes inside the magnet. Some of you may have seen this if you did the lab tour. The cold head is at this end, and gas is circulated by an external compressor at about 1 atmosphere. It goes in, gets pre-cooled, comes along here, and is exhausted up this way and returned by an external pump. And by this means, we can transfer the cooling power here into the sample. And with this device, you can get 1.5 Kelvin if you expand the gas and so on. Now that's possible because we can make a copper shield, which is conduction cooled around everything to prevent any heat getting into the coldest part of the system. On the other hand, if you want to do something a bit further away or with flexibility, then you have a big problem, because the room temperature radiation is 46 milliwatts per square centimeter. You only have 1 watt to start with. So a 20 square centimeter window onto your cold space, you've lost your whole watt. You need to keep it down to a couple of square centimeters. So keeping everything cold is difficult. So if you want to do it remotely and with a flexible line, maybe 2 meters, this is a much more difficult problem. You might think that you could have some sort of shield inside here, but if it's conduction cooled, you may have it cold this end, it won't be very cold at the other end. And so you have to find a solution to this problem, and the main solution is to have an actively cooled shield. So you produce your liquid here, it transmits down a little pipe, it goes to the sample, and then it's returned back down the same line and is used to cool the shield. Now this means you can keep your shield cold, because even with high conductivity copper, we've tried it, it's very difficult to get this end of the shield to a realistic temperature and to make it flexible. Having some flexibility is quite difficult. So that's the way that we are doing at the moment. Even better would be to have means of generating at least part of your cooling at the far end. And there are ways to do that because we can expand the gas at the far end and get refrigerant by this means. So we would want to have compressed low temperature gas, a counterflow heat exchanger at this end, and then returning the warm gas. By this means you could probably generate your watt where you needed it, which would be very, very much better than trying to carry a watt from one end to the other. So this is the sort of thing that we do. And by this means you can obviously avoid the use of liquid helium. All these machines are closed cycle, so there is no losses involved. So thank you very much.
Thank you very much, Jeremy.
Thank you.
Okay, can I invite Eric to come down? Thank you, Eric. So Eric is co-director of the EPSRC National EPR facility and the University of Manchester. So I think you might have come the furthest today, Eric, actually, in this new world still. And he's also on the external advisory board of PEPR. He's internationally leading in EPR spectroscopy applied to inorganic systems. And I'm very excited to hear today about some of the nice work that you've been doing, Eric, on metal organic frameworks.
Thank you very much, Maxie. Absolutely. Okay, but first of all, it's just really, really exciting to be stood at the front of the lecture theatre again. I'm actually quite nervous, and that's really strange. I've not done this in 18 months. Anyway, it's a pleasure to be here for this event, for the launch of the new PEPR Centre. It's a very exciting development. I'm delighted to be involved even peripherally. No, it's going to be great. I work in the University of Manchester, but also I'm associated with the EPSRC National Research Facilities. You just heard a wee mention of the NRFs a minute ago. My own expertise, as Maxie said, is in inorganic materials. I apply EPR across a range of projects there. So I thought I'd just say very briefly a couple of words about some of those projects that I'm more involved in. A long-term interest, for example, has been in molecular magnetism, and particularly large exchange-coupled clusters of transition metal ions, and the weird and interesting and potentially useful physics that arises from those sort of interactions. That has started to take a very supramolecular bent in recent years. This is largely in collaboration with Richard Wimping, his synthetic group. And now we're applying, for example, pulsed EPR methods to measure molecule-molecule interactions in very complicated supramolecular molecules. And one of the things I love about EPR is in the same sort of class of materials, we're using different EPR methods to measure almost terahertzy interactions down to megahertzy interactions. I'm struggling to think of many other techniques that have that sort of range. In the last few years, we've been getting more and more involved looking at F-element EPR. That's both lanthanides and actinides. There are all sorts of important applications down there. That part of the periodic table ranging from magnetic resonance imaging through to the fundamental understanding of the nature of actinide ligand bonding, which is surprisingly poorly understood. And very recently, we've been doing some work on lithium-ion batteries via the Faraday Institution. And this work with Rob Greif in particular, where, for example, we can distinguish between lithium-ion intercalation into an anode material versus lithium deposition, which is also a degradation mechanism of batteries. But the work I'm going to talk about more today is on metal organic frameworks. And if you've not met these before, these are, when I was a boy, they used to be called coordination polymers, but they're called MOFs now. These are very porous, or can be very porous materials where you have organic linkers separating inorganic nodes. This is a particularly well-known and well-studied example based on a zirconium-6 oxide hydroxide core separated by benzene dicarboxylates. And if you get the chemistry right, you get these huge pore spaces in them. And this has led to their extensive study in gas storage, gas separations, particularly areas like CO2 remediation, hydrogen storage for energy uses, and so on. Not much to do with EPR yet, I grant you, but this is where we came in, because we have a very good MOF group in Manchester run by Sihai Yang and Martin Schroeder. And one of the things they've been interested in is using MOFs to absorb, do chemistry on toxic gases. And in particular, we've been looking at them on systems that absorb NO2. Probably don't need to tell you NO2 is the major component of NOx, so an environmental exhaust problem. It's toxic, it's corrosive, it's a greenhouse gas, it contributes to acid rain. It just checks every environmental problem we've been worried about over the last several decades. But the fact that it is corrosive, it's reactive, gives you a problem, because most of the MOFs that have been studied to absorb NO2 are killed by it. You do chemistry on it. And this particular example will absorb NO2 quite highly, but you get this real witch's brew of stuff out the end of it. In other words, it's not a reversible process, that you've got a one-shot material. So Sihai Yang, my colleague, came to us with this material. I won't go into the details of the structure other than to say it's based on aluminium 3+, which forms aluminium hydroxide chains along one dimension of the crystal, separated by these diphenyl tetracarboxylates. And they found that this, I think I got my animation wrong here, has a very high selective and reversible nitrogen dioxide uptake. And the questions were why and how. Now, hopefully any of your undergraduates, some of our undergraduates could tell you that NO2 of course dimerizes, classic bit of undergraduate chemistry. N2O4 is diamagnetic, not much we can do with that. But NO2 is a classic triatomic 17 electron radical. Okay, so could we detect that by EPR? And the short answer is yes. That's the black spectrum here, is the spectrum of NO2. If you're used to thinking about nitroxyl spectra, end spectrum of NO2 is much more isotropic, because that bent geometry allows direct mixture of the nitrogen 2s orbital into the singly occupied atomic orbital. And we immediately know several things we didn't before. NO2 is absorbed, and at least some of it is being absorbed as monomeric NO2. It's not all dimerizing. It's telling us that NO2 is still NO2. It's not reacted. And also the form of the spectrum, this was measured at 40 Kelvin, is telling us about the mobility of the NO2. This is a so-called rigid limit spectrum, so the NO2 isn't moving around through the pores, it's absorbed somewhere. We can then go a wee bit further, because what we would like to know is how that NO2 is interacting with the interior surface of the MOF. So we can use hyperfine methods like ENDOR, which is essentially an NMR experiment on top of an EPR experiment, electron nuclear double resonance. So we can look at, we can bury into the limits of this CW EPR spectrum with ENDOR, and this is in the proton region of the ENDOR spectrum. So we can see the interactions of our NO2 molecule with protons of the MOF. And we can model this, and what we know then, what we can find out is that NO2 is absorbing sort of end-on onto that aluminium, that mu2 hydroxide between two aluminiums. We're also seeing the interaction in this little pocket formed by a couple of the biaryls. So we can actually see where the NO2 is absorbing. This actually has some analogy to how some biologists use EPR to look at substrate binding at an active site. We're doing microwave spectroscopy, so we're sensitive to mobility. So for example, at 40 Kelvin, we're in the so-called rigid limit. As we warm that up, we see it start to average out. This is to do with motion of the NO2. This is anisotropic motion initially, so we can actually tell which way it's spinning, if you like. And as you warm up further, you get a classic three-line spectrum, which is to do with isotropic motion. The NO2 is more mobile now. You've also seen that spectrum broadening, which is to do with collisional broadening between NO2 molecules, between paramagnets. And so there's all sorts of information about mobility in there. This is a slightly different material in which all the NO2 from the same group, in which all the NO2 does dimerize. And I'm just showing you this one then because at one level this is the most boring bit of EPR you've got. You've just got something that's diamagnetic at low temperature because it's all N2O4, but as you warm up, you see the NO2 spectrum grow in. You can do an analysis of that to get at the thermodynamics of the binding of the NO2. So why? What's driving the binding of the NO2 in these very high density storage materials? So there's all sorts of information we can get out. We then started studying all sorts of other chemistry of those related materials over the same system. So for example, the vanadium analog of this, which is redox active between vanadium 3 and 4, does all sorts of weird chemistry, the reduction of nitrogen dioxide or the oxidation of ammonia. This copper dope version does catalytic reduction of NO2 all the way through to dinitrogen. This indium variant, when you grow it on a electrode substrate, is a very good catalyst for CO2 remediation, driving the reduction through to formic acid, a useful feedstock. And I'm not going to go through any details other than all the things I've ringed there are paramagnetic. So there are lots of parts of these processes that you can get at mechanistic information, structural information by the family of EPR spectroscopies. I'm just going to skip that slide, just some more examples. These are the people that did that work. The MOF materials came from Seehei's group and Martin Schroeder's group. Floriana and Elena led most of the spectroscopic work, also with Zi Wang and Lili Li, two PhD students. And these people, most importantly, the EPSRC for the funding of that work. Now, I just wanted to say one word I've gone red. Sorry, Maxie. 1 minute. As I said, we run a national facility at Manchester, and I just wanted to say a little bit about the relationship here. We're in no way in competition with what's happening here. EPR is a very, very collaborative area, and there are huge numbers of people across this country and internationally who have materials that want to be studied with EPR, but don't maybe have the expertise or indeed the infrastructure to do that. So there are experiments that we can do at Manchester, for example, at other frequencies perhaps, complementary to what happens here. But the reverse is true as well, and Max has already mentioned these, but you look at what they've done recently, particularly in the area, for example, of electrochemical EPR, what John's been doing with instrumentation, and then it's really exciting to see these ideas being brought together in applications in, for example, biochemistry. I look forward to seeing what else is going to come out. I wish you the best of luck. I know it's going to be a success, Maxie, and congratulations on your centre.
Thank you so much, Eric. So with that, I'd like to invite Andy, who is joining us online, Dr. Andrew Ashley, one of my colleagues here in chemistry, who is doing some very exciting work in the activation of dihydrogen and dinitrogen. And I believe, Andy, you're going to be telling us some of what you'll be doing with the latter, so nitrogen fixation, and also some applications of EPR in this field.
Hi, I'm hoping that you can hear me, yes? Yes. Okay. Well, thank you very much, Maxie and the organisers, for giving me the opportunity to speak at this wonderful event today. So we in our group have been investigating some very simple iron phosphine complexes for the fixation of dinitrogen. And today I'm going to be able to tell you about how EPR has basically been quite instrumental in being able to resolve some of the speciation that occurs in this really quite complicated reaction. Okay, so nitrogen is an essential element in its monatomic form for life on this planet, and that's because it is the constituent of amino acids and nucleic acids, which form proteins and DNA and are the building blocks essentially of life. But nature sort of played this cruel trick in that nitrogen obviously is, whilst very abundant, is tied up as its diatomic form. So it's biologically unavailable and we have to fix it. And so the key route is to actually make ammonia. And this is such a pivotal process. It's almost half of life on Earth, of human population, wouldn't exist if we didn't have this reaction, because the ammonia makes fertilizers, which enhances agricultural yields, thereby enabling more of us to essentially survive. But as I said, it's a conceptually simple reaction. You just react 3 molecules of hydrogen, or if you look at the way that nature does it, it's using proton-coupled electron transfer, 6 protons and 6 electrons. But of course, the issue is, so whilst thermodynamically this is viable, kinetics obviously say this is going to be difficult. And that's ascribed to a very large bond association energy. It's a very strong triple bond. You have a very large homolumin gap, which means it neither wants to react with nucleophiles nor electrophiles. And there's no dipole moment, and this should be contrasted with the molecule CO, which has an even stronger bond, yet participates in myriad reactivity in many industrial processes. And so why study homogeneous ion complexes? Well, iron actually occupies quite a privileged position. So humans fix nitrogen over an iron catalyst using the Haber-Bosch process, and this is conducted on an extremely vast scale, albeit under very, very harsh conditions. Conversely, nature adopts nitrogenase enzymes, and iron is common to all of the 3 main nitrogenases known. So iron is a good place to look, but what are the motives? Well, we have to be honest with ourselves. It's very unlikely that if we discover a good process for nitrogen fixation using solution phase complexes, that it's going to be able to compete with the Haber-Bosch. The Haber-Bosch runs at nearly 100% thermodynamic efficiency. But nonetheless, this is a very complicated and very challenging reaction. And just to put this into perspective, you have to break 3 nitrogen-nitrogen bonds. They're very, very strong. And you then have to selectively form 6 new nitrogen-hydrogen bonds, all on the same catalyst. And so for that to remain intact is quite a big ask. But fundamentally, homogeneous complexes allow us to understand this mechanism because they're much more amenable to spectroscopic study. And so we embarked upon this compound, and this had been known for nearly, it's almost 30 years old. And it's very simple. It's made of a commercially available diphosphine and an iron precursor. And in 2 very simple steps, you can access gram scales of this compound. And so this reaction on the top actually exemplifies what chemists working in this sphere actually try and achieve. You subject your catalyst to a cocktail, if you like, of excess protons and excess reductants. That's a source of electrons. And so what we're doing is we're adopting effectively a biomimetic strategy. And this allows us to operate at really low temperatures. Now, at the time that we published this was one of the most efficient nitrogen fixation catalysts out there, albeit it's only 25 molecules. And what we managed to do, though, is all previously documented compounds could only use much stronger acid sources and stronger reductants than the ones that we could employ. So there was a net energy saving, if you like. And the reaction scheme on the bottom shows exactly what we're doing. So you've got an acid and you've got an electron source, and what they want to do is they want to form dihydrogen. But of course, we circumnavigate this through the use of the catalyst, and nitrogen instead is selectively reduced at the metal center, giving us an amine product and the oxidized reductant. But what was quite surprising, and still is for to date, is that this is really the only catalyst that seems to be selective for hydrazine production. And so why is that unusual? Well, it's because the direct conversion from nitrogen to hydrazine is extremely endergonic. Okay, this is a really unfavorable reaction. So we thought this is something quite dramatic. And there's no commercial process from nitrogen directly to hydrazine. So instead, what humans do is we fix nitrogen all the way to ammonia and then oxidize it back up using some quite nasty chlorine-based oxidants, which is obviously wasteful, but more importantly, you're wasting an equivalent of hydrogen. And the reason that that's bad is because hydrogen still is currently expensive. So we sought to understand what the mechanism of this reaction was. And what we did is we took our tube with our compound and we subjected it to a continuous wave EPR, and we got this signal. And the reaction went from a lovely orange to quite a bright green. And so we could simulate this, and it's a single electron, unpaired electron species. So that made us think, well, we're starting with ion 0. Maybe we're dealing with a compound that's actually of the oxidation state ion 1. So we start with 0. We can use a chemical oxidant in a controlled fashion, and we can form this ion 1 dinitrogen species, which is also green. And we have the crystal structure. We've omitted the anion here for clarity, showing what it looks like. And so when we took the EPR spectrum of this compound, it gives a very, very similar signal. And so that led us to speculate, well, actually, is this ion 1 compound part of our catalytic cycle? And so on the top left, you can see a continuous wave spectrum of this ion 1 dinitrogen compound. And what we found was that this green species can actually lose dinitrogen to form this really quite coordinatively unsaturated, beautiful blue ink color, whose EPR spectrum is shown at the top. So it's quite a diagnostic change, and it turns to a more rhombic signal. And actually, this compound is so sensitive to nitrogen, you can see that where they don't actually overlap, this corresponds to some of the dinitrogen compound impurity in there. And that's even within an argon glove box. It will pull the nitrogen through the gloves. And so what was perhaps more surprising is that this reaction actually happens in the solid state. So we have a powdered sample of this base-free ion 1 species with its characteristic rhombic signal. You then admit nitrogen and you get quantitative conversion to the dinitrogen species, the top right. And then if you evacuate, you get almost complete restoration of your original signal, showing that you've reverted this process, and it's fully reversible. You can cycle this several times over. And we believe that the reason this can happen in the solid state is because there's very little geometric change for the iron phosphine platform upon dinitrogen binding, because we are effectively square planar going to a square base pyramidal species. And so then we thought, well, if we can get nitrogen reversibly bind to this platform, what happens when you add hydrogen? The ultimate goal would to get, rather than using protons and electrons, using hydrogen to actually reduce dinitrogen in a catalyst. And so we've got two options here. We had this reaction and we went from this blue to another green coloration, slightly paler than when you use dinitrogen. And the two options are, is it actually this compound on the right hand side, which is an oxidative addition ion 3, or a much rarer, and in fact it's incredibly rare to get, dihydrogen as with the bond pretty much still intact, bound to a paramagnetic ion center. Now the problem with this species is we couldn't get the crystal structure. So in the absence of solid state structural data, we had to employ different techniques. So on the left hand side you have this continuous wave spectrum, which fits very well with the experiment and with the simulation. But with continuous wave, a lot of information is buried here. So this electron is coupling to all the other spin-active nuclei in this compound, and that includes the hydrogens and the phosphorus. So what we wanted to do was disentangle the information here, and that's why we moved to a technique known as Davis-Endel, where we can actually extract the proton coupling from the hydrides to the ion center. And so we could use another technique which deals with the hyperfine interactions to get even more information, and we actually labeled, rather than using dihydrogen, we used deuterium, and we could allow this simulation. This is a technique that is rather complicated, and I'm told that where the red blobs match the black blobs, that's a good sign, and it also means that our DFT, we could use computational calculations to simulate this to get a good fit. And that allowed us actually to obtain even the ion-hydrogen distance because of this unpaired spin on the ion coupling with these hydrogens. We can get this dipolar interaction. Furthermore, what we can do is we can use this angle beta to see, so the longer the hydrogen-hydrogen distance, basically the wider the angle, so smaller angles would be more indicative of the species that we have here. And with a beta of 6, that means that actually we do have a very, very rare example of a sigma dihydrogen complex. And very, very recently, we've discovered that this compound can actually act as a hydrogen atom source, as a reductant, or a proton source. And so efforts are ongoing to see how we can tie this in to dinitrogen fixation on this platform. And so in summary, I hope I've shown that this iron zero compound is a very efficient catalyst for nitrogen fixation, or it's certainly a pre-catalyst. We see that there's an iron 1, so paramagnetic species are clearly involved during these this conversion. And this platform both reversibly binds nitrogen and dihydrogen. EPR was absolutely critical. It was pivotal in being giving us a technique to be able to understand this structurally in the absence of solid state data. And it's a rare example of an open shell dihydrogen complex. And so this begs the question now, we've got iron DEPA, we know this platform allows us to do the nitrogen to hydrogen fixation. We also know that it binds nitrogen and activates dihydrogen. And so can we actually combine all of these things together to get a direct nitrogen hydrogenation catalyst under mild conditions? And so in summary, these are all the people who've given us the money to enable us to do this. And importantly, these are the students that enabled this to happen. And I'm very thankful to Dr. Will Myers, who did a lot of the EPR work. All these compounds are extremely air sensitive, which means that you have to do this on site and ask people to borrow their glove boxes and equipment up in Oxford. And now with PEPR, we can do this in-house, and that's really going to be game changing. So, and I'd like to thank you all for listening. Thank you very much.
Thank you so much, Andy, for joining us online. And now we have, well, just 6 minutes or so for Q&A, perhaps a little bit longer if we need to. And I think, Alberto, you're moderating the questions. Have you got some coming in? No, no one asking anything. Okay, well, if you'd just like to raise your hand, that's also fine, as I said earlier. Any questions? No, no one's got any questions? George, yeah, I think either you have to shout or go down to the microphone if you don't mind. If you could say who you are as well, that would be great.
I have a question. Hello? Yes, perfect. Regarding the cryogenics, any chance we can move this also to NMR?
I think, Jeremy, you're best placed to answer that. Maybe if you just stand on that microphone there, that would be great.
Yes, we certainly do. make magnets that run without liquid helium. And compared to a conventional NMR magnet, because the current leads are permanently installed, there's no need to take them out because we're not worried about small heat loads. That allows us to change the field at any time. So that's quite an attractive feature for some people. So we are making quite a few of those. Yeah.
Perhaps I can add one thing to that. I believe now there's also quite a lot of extension for the magnets that are superconducting, right? To actually have those on cryogen-free systems. So that also applies to high field EPR. So I think that's all quite exciting moving forward. Yeah. Anything? No? Okay. Well, I have a question for you, Eric. I love all this WOF work, I have to say. I think it's fantastic. I just had, I was wondering with your spinning, not that it really matters, I suppose, like in terms of, I guess, the output, what the WOF does, but I thought it was really intriguing that it spins in one direction. So can you tune that with how you design the WOF? Have you looked at that?
The short answer is no.
Okay.
I mean, unsurprisingly, perhaps you've still got kind of a long axis and it's spinning around that long axis. But if you go back to there's early work by Jack Fried, perhaps unsurprisingly, looking at NO2 absorption of glass, and he saw similar. He did quite a lot of work modeling that in a motion model. I'm not sure what temperature is. At the moment, it's an observation.
Yeah, it's quite intriguing, isn't it? I think. Yeah, please.
Just a quick note to say, we could use the microphones for our online audience. They're going to struggle to hear.
Okay, I can try and repeat briefly. I suppose what you said, Eric. I think the short answer is no. He said, but there's early work by Jack Fried investigating the rotation of molecules in that sort of environment, although not really exactly what you've done, of course. Anyway, I think probably we will leave it here and then start the break a little bit early, just 3 minutes early actually, or rather perfectly running on time. So we've got a 20-minute break now until 3:20. So if I could all invite you back in time to continue our next session, that would be fantastic. Thank you very much. Okay, welcome back everybody, and welcome to our second session where we are switching gears a little bit here now, and I think I called it energy and environment, more loosely speaking. And it's my pleasure to introduce to you another co-investigator of PEPR. This is Professor Anthony Kucernak, who is a world leader in the application of electrochemistry to a diverse range of systems, especially in the field of electrochemical power generation and storage. He's filed numerous patents and got 3 spin-off companies. And I think what we're hearing about today is also a little bit about the work that he's been doing very hot off the press with Alberto, which of course I'm very pleased about. So the floor is yours. Thank you.
Okay, thanks a lot. And thank you very much for the invitation to actually speak here. Actually, I've probably got to stand here because I've got to stand and look at the camera. Yeah, so I suppose this is very timely actually, because the work I'm going to talk about is something that we hadn't thought about at all when the application went in, and it's something that's actually happened subsequently to the instrumentation arriving in the department, and it became an opportunity. And what I'm going to show you is some results that are sort of fairly hot off the press. Experiments were only finished beginning of last week, so nothing's been published at the moment. In some ways, it's utilizing EPR. You know, we're not going to see the sort of beautiful spectra that we saw earlier on. Actually, what we're using the EPR spectrometer here is more as an analytical instrument in order to determine something about what's happening within a real system. But the really important point about these systems are that they're real-world systems. You know, they've actually got quite high concentrations of active species, so they're actually quite difficult to study in other methods, using other methods. So, just wait to go to the next slide. Oh, I've got to use that. Okay, thank you. Okay, so we're all familiar with the intermittency of renewable energy. You know, the issue that has. The UK's got a bit of a problem with it at the moment, even because of the problem with wind energy not being as much as it might be expected. The graph down at the bottom right shows what might be expected in California in 2045, where you see that a lot of renewable energy is made in the middle of the day in terms of solar energy, The dotted black line is associated with the requirements of energy in California. And you see that in order to utilize that renewable energy, you've actually got to shift half of the renewable energy from the middle of the day to the night. Okay, and that means you need some sort of electrical energy storage system. The graph on the left shows us what the current pumped hydro, the way we store electricity at the moment is pumped hydro. Got about 160 gigawatts worldwide, about that, at the moment. By 2030, that's liable to increase by 38%. We're somewhat limited by putting in extra pumped hydro because all of the good sites are already gone. Over that sort of same period, electrochemical energy storage, and by that we mean batteries, are going to increase from about 2 gigawatts to about 175 gigawatts. You see there's about an 8,000% increase. So there's a massive demand for new electrical energy storage. Of course, one possibility might be to use lithium batteries. We've already heard about lithium batteries, but the problem with lithium batteries is that they're not going to be inexpensive enough in order to store this sort of electricity. In fact, lithium batteries will probably be about 100 times, even at their lowest cost, sometime in the future, they'll be about 100 times too expensive in order to store the electricity, for the significant periods that we might need to do. So an alternative technology to that is what's called redox flow batteries. Redox flow batteries are large-scale battery systems. In the upper right-hand corner, you see the breakdown of a redox flow system. The difference between a redox flow system and a typical battery is that instead of having all of your reactants within the battery casing, the redox flow battery utilizes two electrolytes which are contained outside of the actual battery casing, and you flow those reactants through the actual device. And of course, there have been some examples of relatively large-scale ones. Just to point out, this 120 megawatt-hour plant, Little Bartford, 2002. That was a plant that was being built just quite close to Bedford, and those two big black tanks that you see were actually for the electrolytes used in the redox flow batteries. And the stacks to the right of that, the blue and the white thing, is what the stacks in the white building behind that, where all that electricity was going to be stored. In principle, you can have a whole range of different redox couples. This sort of diagram here shows all the different redox couples you have. And in a redox flow battery, you actually couple two different redox couples, so one in one tank and one in the other. The most common one is your vanadium system, which utilizes vanadium 2,3 by the blue line on the left, and vanadium 4,5 here. We're going to talk about a different battery system, which is the one we're developing, which is based around hydrogen and manganese. One of the nice things about the vanadium system is that you might imagine that if you've got some catholyte here that leaks through your membrane and gets into your analyte, if you've got an all vanadium system, that doesn't really matter because you've still got vanadium. But as soon as you've got redox couples with different elements in them, then potentially you end up mixing your electrolytes in your two different tanks. And as these battery systems are meant to last 10 or 20 years, even though you might have a very slow rate of permeation, that becomes an issue, once you get up to 10 years. So we're using manganese. Why do we want to use manganese? Well, manganese is the 12th most abundant element on the Earth. It's relatively biologically well tolerated. It's used in a number of enzymes, of course. Each household actually contains about 1 kilogram of manganese in the form of zinc alkaline batteries, so there's already a lot of it around. And the other major reason is because of the low cost. So manganese, we could actually have an electrolyte that costs less. And today we can make an electrolyte that costs less than $10 per kilowatt hour. So that's a factor of 10 less than the eventual lowest cost that lithium might get to. And because redox flow batteries tend to last at least 10 times longer than lithium batteries, you get 10 times more cycles out of them. That means your cost for energy storage is about a factor of 100 down. There's a problem with manganese though, and that is that once you form manganese 3, it's actually unstable in aqueous solution. It undergoes this disproportionation reaction, this red reaction, the lower right-hand corner, and it forms manganese dioxide. And so if you actually make a 1 molar manganese 3 solution, within a couple minutes, actually, you've lost most of it. It's already disproportionated to manganese dioxide, and you end up with a solution that contains a sludge of manganese dioxide, which isn't very useful. What we've done is we've developed a modification to that electrolyte by including titanium-4 in that electrolyte, and that actually helps stabilize the manganese 3 in solution. In fact, it doesn't appear to entirely get rid of all of the colloids that are formed, but it actually stabilizes the colloids in very, very small nanometer sized particles. And we sort of want to study this process much more. But this electrolyte, which is with titanium, what this looks like, I should say, with this electrolyte, you can then form manganese 3, which is actually stable for hundreds of hours. Okay, so that's sort of the really nice thing. Once you include titanium-4 in the solution, you actually stabilize the manganese 3. And we can run a redox flow battery for hundreds of hours, for hundreds of cycles, 700 cycles. Here's a system running for 700 cycles over 3 months, with no degradation of performance. So that's all fine, but we don't exactly know what's happening in the electrolyte. We don't know what the speciation of the manganese 2, manganese 3, and also the manganese 4 species, because we do realize there are some manganese 4 species being produced in solution. So the first thing we did was to try and look at the manganese 3 in solution. You can follow manganese 3 by using UV vis spectroscopy, because manganese 3 has got a very strong absorption in aqueous solution at around 500 nanometers. And we can actually study that, and from that we can actually look at the concentration of manganese 3. That works pretty well up until a certain concentration, until we charge the battery to a certain point. But then beyond that, we start getting interference from the sort of colloids which are produced in the solution. At this point, the EPR system was installed in the department, and we had this great idea. Well, it's a bit difficult to follow manganese 3 across all of the concentration range, but why can't we use EPR to follow manganese 2 and actually see the opposite case? And of course, manganese 2 is a nice EPR active species. We can actually follow it at high concentration. I should say concentrations of, I didn't actually mention the electrolytes, but you might have seen earlier on, these electrolytes are actually quite acidic. It's 5 molar sulfuric acid, 1 molar manganese. So that's actually quite concentrated. And Alberto did a marvelous job in trying to help us, and we've been able to actually study, look at charge and discharge of our system. So here is, here's our resonator. We can actually see here's our electrolyte, and here's our battery charging and discharging. Here's our manganese 2 decreasing in concentration and increasing as a function of charge and discharge. And we're sort of analyzing these data. We're able to study the disproportionation reaction, because we can see the amount of excess manganese in solution from what we expect, and we can also compare that to thermodynamic calculations of what we might expect from the battery. We can also follow the kinetics. So this is using the EPR to actually follow the kinetics of this reaction in red at the top. So the really nice thing of what we can do now is we can actually study the entire speciation of manganese 2, manganese 3, and manganese 4 as a function of state of charge in our battery, and that's something that we couldn't do earlier on. So with this, I want to thank the people involved on the project. So Ben Simon up there on the left-hand side is a PhD of mine, and he's working on redox flow batteries. Alberta, of course, has done a marvelous job in helping us get this all set up. And I should say that this technology has been spun out to a company called RFC Power, who are actually developing this for grid-scale energy storage. And with that, thank you very much. Sorry for overrunning a little bit.
Thank you so much, Anthony. So time for a little Q&A. Do we have any questions from the audience here in person, first of all? There's Adam at the back. So Adam, if you could come to the front, please, and speak into the microphone, if that's okay. And also just to remind people asking questions, if you could just say who you are, that would be great.
Hi, I'm Adam Sills. I'm a PhD student here at Imperial. I have a question for you, Anthony. You present these really interesting batteries, and I just sort of wondered, you might have quite a lot of aqueous metal waste on quite a large scale, and that might be a sort of ecological problem. So I wondered what makes, if that firstly would be a problem from a waste disposal perspective, and secondly, then if so, what makes this system better than, say, some other energy storage techniques, such as sometimes you can pump water up a mountain, for example, to give it potential energy that can then be put back down and run through a turbine. So I just wondered your thoughts on that, please.
Okay, thanks, Adam. So in my first few slides, I actually talked about pumped hydroelectric and the requirements, and that we already have a lot of pumped hydroelectric systems at the moment. The issue is that we're limited in terms of geography. So most of the obvious places you'll put pumped hydroelectric are already being used at the moment. Pumped hydroelectricity does actually come with ecological issues as well. Actually, there's quite a lot of CO2 emission that comes due to rotting matter. But anyway, that's something else. In terms of recycling, you're quite right. End-of-life recycling and reuse of materials is a big problem for any sort of battery system. For lithium batteries, it's particularly difficult because all your materials are actually in intimate contact and intimately mixed. For redox flow batteries, it's somewhat easier because, of course, all of your electrolyte is present in a big tank as a solution, but it's much easier to actually then take that and actually deal with it. I mean, one of the issues, for instance, with normal batteries is you have to try and shred them up and then chemically extract all of the material from them, and that's actually quite an energy-intensive process. Whereas if you just start off with a solution of metal ions, then it's much easier to, get the metal out and then recycle it.
Thank you. Any other questions from the audience? Yes, please.
My name's Soren. I'm a postdoc here at Imperial. I wanted to ask Anthony, I'm very intrigued about this phenomenon that titanium stabilizes the manganese 3+ in solution. Can you elaborate on what you think the mechanism is, and is the titanium used up in the process?
I had exactly the same question. Thanks for asking it.
And it's a very good question, and it's an outstanding research question for us to try and actually study that and understand that. We've done XAFs on these electrolytes to actually see what we can see from the titanium edge and the titanium extended structure, just to see if we can actually understand that. At the moment, it's really difficult to actually understand what the titanium isn't used up. The titanium is a bystander. I suppose our hypothesis, or my hypothesis at the moment, is that because we still appear to have some sort of colloid formation, the titanium appears to limit the growth and aggregation of those colloid particles, so that the colloids are actually kept in sort of nanometer size and remain in solution, so you're probably producing manganese 4 in solution. We know we can actually overcharge these electrolyte up to 2 electrons per manganese, so we can actually go all the way up to manganese 4 and still have a solution which is stable that we can then. So it looks like the titanium probably sits on the surface. This is my hypothesis. The titanium sits on the surface, acts as a terminator on the colloid, and stops further aggregation and growth of those colloid particles. I should say that we've kept the electrolyte's been stable for 50 days, fully charged, and it doesn't aggregate. So it's sort of quite interesting, but it's actually very difficult to study this in such concentrated electrolytes. That's the issue we have. As soon as you try and dilute the electrolytes, the chemistry all changes. Okay, so that's the reason why we needed to use something like EPR, because we could actually study the electrolyte at full strength.
Thank you. I think last question from you, Bill, please, and then we move on.
Just carrying on the same business. Why did you try that metal in the first instance? It seems an odd choice? Did you try a whole series of things, or was it by chance?
So there were some indications in the literature that titanium was interesting, but we also tried a whole range. But we also tried a whole range of different metals as well. But titanium is, you know, the best. It's a little bit more expensive than manganese, but you know, it works.
So what else worked? Can you work it out from what else worked?
Maybe. It's difficult. Yeah.
Okay, thank you so much. Nice to have a bit of a discussion going. That's great. So can I now switch gears a little bit to materials and invite Sandrine to come down? So Sandrine Heutz is also a co-investigator of PEPR, but she's also the champion of SpinLab, a complementary facility in South Kensington, which is very well geared up for looking at spins and different angles. So I think we really have some nice collaborations there. She's also the co-director of the London Centre for Nanotechnology. And she is, I think your research focus, Sandrine, is on functional molecular materials for sustainable and efficient technologies. And I look forward to your talk.
Okay, thank you very much, Maxie, for the kind introduction, and congratulations on fabulous setting up fabulous facility already, and a great event. It's really good to be standing at the front of a lecture room for the first time in 18 months. So thanks. Okay, so I will talk about molecules here, and the type of molecules that I want to talk about are molecular semiconductors that have known a lot of success already in optoelectronic devices, such as displays, and here is an organic light emitting device TV, some of the more expensive but highest contrast for brightness, Apple Watch, and the Nintendo Switch, which is not out yet, so you know, very desirable products here. Now, the principle that dominates these kinds of devices is that you're putting in a charge, and you are, or two charges, an electron and a hole, and you get photons out. Those molecules, those molecular semiconductors, can also be used for solar cells, where the opposite process takes place. You're getting light in and you're extracting charges. The beauty of the molecules is that they can be simply printed. So, you know, some of them are dyes like you would use in conventional printers. And so you can put them on flexible substrates. They're conceptually very cheap, etc. Looking at exploiting just the charges here, you could also think about biosensing. Some of those molecules are inspired by chlorophyll, and here artificial skins. And some of those foils have been put in the heart and the brain, etc. So lots of things going on there with charges and photons. Now, of course, those charges and the photons also have a spin, and I was showing there just the charges coming together to let to relax into a photon for an OLED, but that depends on the spin of those charges as well. So this is where EPR starts to come in. And if we want to take those molecular materials one notch further to the latest technologies that get us all very excited, then you know, looking at memory, for example, that previously was just based on charges throughout the transistors. Well, now the most effective memory devices would be based on spintronics, for example, and then quantum technologies as well, quantum computing, quantum sensing. I'm sure we'll hear quite a lot about that from John Morton coming next. Now, talking about our research, I want to focus on two key problems that we've been working on that involve spin in the context of molecular technologies. The first one is based on pentacene, where we want to use spin to improve photovoltaic performance, so how much current we can get out of a solar cell. And the second one is to exploit some of those molecules that are used in conventional solar cells and show that actually they could be used in quantum applications. Okay, so first, the improving PV efficiency. This can be done if you think about the PV process, where a photon is used to create a pair of charges, Well, actually, if this photon could be transformed into 2 photons, then you could double the amount of charges that you could get out of your device. And this is the process of fission, where a singlet will be, where a photon will create a singlet, and this singlet will be separated into 2 triplet states if the energy levels are favorable. And you can see from the diagram here that this can happen if you've got 2 neighboring molecules, and basically the excitation can be shared by the neighboring pentasines. Now, at the end of this process, you get 2 triplets that can be separated and forming charges, but the mechanism by which this happens is very mysterious, or has been very mysterious, and a lot of these processes are spin conserving, but a key intermediate is actually a quintet state, and that quintet state can be seen using EPR spectroscopy. So finding that quintet has been a big challenge, and various research groups have been looking into this. A group with Dane McCamey over in Australia has been looking at dimer molecules, where you can therefore bring the 2 pentasines in close proximity, and they've seen that actually you can get some quintet intermediates at very low temperatures, but this is not really a thin film scenario as you would use in an optoelectronic device. The group over in Cambridge, Richard Friendly, Roessler et al., have been looking at TIPS pentasine films. They've also seen the quintet, but also in amorphous structures and at very low temperatures. So my research group is really focused on developing methods where thin films can be designed to really address questions about sort of fundamental mechanisms for optoelectronics and spintronics. And so we've been looking at diluting pentasine in a terphenyl matrix. So this is a wide bandgap matrix. You can't photoexcite this molecule at the same wavelength as the pentasine. Crucially, those 2 molecules crystallize in about the same structure, and so you can co-evaporate them in a high vacuum organic molecular beam deposition chamber and get a statistical mixture of both molecules. And this is really the work that was driven by Daphne Libert-Perkel and also with EPR expert Enrico Salvadori, who's received, of course, excellent mentorship from Maxie, Chris Kay, who some of you in the EPR community might know, and also John Cook Kim on the growth. So firstly, we can see that we are able to really address those individual spins, the individual molecules. If you excite just an isolated pentasine in this crystalline matrix, then you will see just the isolated triplets. And you see from the powder spectrum on the left, compared to the oriented film. In the oriented films, you can really see the specific transitions along the long axis in this case of in this case over here versus the XY transitions. So we worked on this X configuration. So this is really a very nice way to be able to address specific transitions. And we looked at the concentration dependence of the pentasine within the terphenyl matrix. The goal there was to really trap this fission process and really trap the quintet states. If we start at the top at very low concentrations, we've got isolated triplets. So there's just this free triplet state, which people know quite a lot about. So this is the intersystem crossing from the singlet to the triplet. If we increase the concentration of triplets, of pentasine, and here the limit of fully dense pentasine films, all of those triplets have disappeared because they have annihilated, they've collided, or they're just diffused, they're diffused too far away. The sweet spot is in the middle there, at about 10% concentration, and you see the grey shaded area. This is where the quintets are starting to appear, and this is those triplet states that are formed by fission and are very close together. So from this work, Daphne and collaborators were able to really understand the mechanisms by which this fission proceeds. And so this is the time after photoexcitation. And you see that, first of all, you form your quintet, but from parallel molecules that are parallel to one another. So there are two different kinds of environment as well, which was very important for us to understand. If we then look further, then at longer times, you've got the triplets, the free triplets forming. So that's from the outer peaks, but also the quintets that are being formed from the herringbone structure. These will then separate, and you've got dissociation into free triplets. But what's interesting to note is that you've also got an equilibrium in the herringbone structure that is still coupled. Okay, so we see two different types of environments in those pentascenes. And the ones that are coupled are favorable for memory and logic. And this is something that we also want to exploit in a range of different settings, for example, interacting with plasmonic nanoparticles with Anthony Mao. I'll very quickly go to PV for quantum. We've looked at this, so this is now based on the phthalocyanine. We don't need photoexcitation there, so this is work that's been done a longer time ago. We're trying to use the copper spin, the spin 1/2, as the quantum bit of information. And again, we're using this co-evaporation with metal-free phthalocyanine. We were there really interested in not only knowing the environment of the spins, but also exploiting their spin lifetime. And lots of very nice work there done actually at UCL with Chris Kay, Mark Warner, and co-workers. And what, cutting a long story short, we see very long T1s and T2s. There were, at the time in 2013, quite competitive with other types of materials, and we've seen some very nice single molecular magnets flashed in Eric McInnes's talk. So they are great in terms of lifetimes, though there were still some gains to be had from those films, and especially they're fairly easy to process. Just to finish, recently there was some really interesting work to show that the vanadium phthalocyanine works quite well at room temperature. So this is from a group over in Italy, and this, so all the work that I've shown you before was done in collaboration with UCL, and as Maxie very kindly mentioned, now we've got the facility of EPR at Imperial in SpinLab, so we've got a CW spectrometer there where we could again play those tricks of co-evaporating vanadium phthalocyanine and zinc phthalocyanine, and to show these orientation dependent, to show that we can address these spins separately. And Irina Nevjestik, who's running SpinLab, is here today, and Harry as well. So to conclude, putting back where we were, I hope I've shown you that exploiting the spin in molecules is possible. Continuing this work, I hope that, I really look forward to working together with PEPR to carry on this research into exploiting those spins in molecules. I've got to thank a whole load of people. The key ones were on the slides, and I thank you very much for your attention. Sorry for running over.
Thank you very much, Sandrine. So again, please save your questions for the Q&A session in just 10 minutes. So I'm happy to introduce our next speaker, who is Professor John Morton from UCL, also a co-investigator on PEPR. He's built 4 pulse EPR spectrometers. I think that's right, John, isn't it? And he's made significant advances in the field of pulse EPR. He's researching the sensitive readout of spins in molecules and materials for applications in quantum computing and quantum sensing. And what we'll hear about today, I think, is some of his contributions to that, as well as the instrument development side of PEPR that I already mentioned at the beginning. Thank you, John.
Brilliant. Thanks very much. I'm not mic'd up, so I might just have to shout. There's a mic. And does this work? Yes. Great. Excellent. Well, try standing here. We're on the X. So I'd say it's a huge pleasure to be here. I think this is my first in-person talk for something like 18 months. And I don't know about the rest of you, but I'm fed up of lecturing to a computer screen. So at least this way I can see you doze off, even in the short 10 minutes we have. It's a real pleasure to speak at this event. I'm sorry I missed some of the earlier talks. So let's crack on. As Maxie said, I'm going to speak about not just the applications of ESR for quantum technologies, but also how some of the methods and ideas from quantum technologies have started to come back and help add some performance for different types of ESR experiments. So you probably heard quite a bit about quantum technologies. I'll throw up a few different quotes here to set the scene. You've got Paul Davies saying that he believes that the 21st century will be known as the quantum age, and Mike Lazaridis, who's the founder of BlackBerry, if you remember that, saying that reading about quantum entanglement was like reading about a manual that had fallen from the future. And the way I like to think about this is that at least when I learned about quantum mechanics at school and university, it was a lot of what we were learning was what quantum mechanics told us wasn't possible. Through, for example, Heisenberg's uncertainty principle, you can't know the position momentum of a particle with arbitrary precision. But now we've come to understand through what we call quantum technologies, fundamentally new ideas, new phenomena that are new technologies that are enabled by quantum mechanics and not constrained by these old laws of physics. And primarily these fall within three categories: quantum computers and simulators, quantum sensors and standards, and also quantum communication. And you probably will have seen quite a bit of quantum computers in the news. You've got headlines such as, so this from the New Scientist, that quantum computers will break the internet. You've got this claim from Google that they've demonstrated something called quantum supremacy, along with a picture of their CEO touching the fridge. I'm sure there's a PhD student behind him waiting with a bottle of IPA to quickly wipe that off, because you shouldn't be touching the fridge really. But and what this was about, I like to draw parallels with the famous game between Kasparov and Deep Blue. If you remember that, this was the incumbent technology for chess, the human brain, competing against the new technology, which was this classical computer called Deep Blue from IBM. And famously, in that series of matches, Deep Blue won. And what we had a couple of years ago was a similar game. It wasn't a game of chess, but it was a problem that had been constructed. In a sense, the problem was, can you pretend to be a quantum computer? But it was a well-defined a computing problem. And the incumbent technology here was Summit, the world's biggest supercomputer, made coincidentally by IBM. And the new technology, which was this quantum computer, was a 50-qubit chip from Google called Sycamore, and there the Google chip was able to comprehensively win. So this stuff is happening. This was a toy problem, a bit like chess. It's a game, but it's beginning to reach a level where it can outperform conventional computers, and we hope soon lead to applications. There's also different ways to build quantum computers. The examples I showed you were qubits made from superconducting circuits, and as shown in this buyer's guide from the New Scientist, there are other types of qubits that also score highly, such as spin qubits. So the kind of things that we would use ESR for this for the development of this technology is to study source of decoherence. So in these superconducting qubits, the materials, the interfaces are critically important in determining the error rates and determining whether the computer can run properly. But of course, there's also the opportunity to use spin itself to encode quantum information. And there, of course, studying the coherence properties of the spin is critical. You can identify new types of spin qubit systems and do a huge amount of the foundational work using ESR. And you can also build on existing ESR techniques and new ones to develop new protocols for controlling quantum information. So just going to highlight a few examples of this in some recent work from the group. Many of you will have heard about phosphorus-doped silicon. Aside from being, of course, a cornerstone of the semiconductor industry, it's been a long-standing study for a while as a potential qubit. Here we're interested in a a slightly different donor. It's in group 6 of the periodic table, so it's actually a double donor. At room temperature, it's putting 2 electrons into the conduction band. If you cool it down and play some tricks, you get it into the singly ionized state, and then there's a single bound electron. It becomes isoelectronic with phosphorus, and with that single spin 1/2 and the nuclear spin of the tellurium, you can have a bit of fun. And we were exploring this as a potential qubit system. What makes it interesting? Well, often you get band bending of silicon near an interface, and that ionizes the phosphorus and you lose your spin. So this being a much deeper donor and a double donor means it can retain its spin even at very shallow depths. I just want to highlight here, I think Maxie said something about the sort of new instrumentation developments. These are, what I'll be showing is data from very shallow films, just 20 nanometers depth of ion implanted. The concentrations of activated spins are not particularly huge. They tend to the 16 per cubic centimeter, but over a very shallow depth. And the only way that we could get these measurements to work is using this sort of cryo probe. But yeah, we looked at the spin transitions in the system approaching zero field. You can see you can do ESR even at zero field at around 3.5 gigahertz because of the large hyperfine coupling. And you can look at SX and SZ transitions. You can look at the line widths of this system and see how they narrow up as the first order field dependence goes to 0. And you can measure different, you can measure T2 under different conditions. In these cases, we found it was limited by the silicon 29 in the natural silicon to about a millisecond. But anyway, all of these measurements, although with a cryo probe with this copper loop gap resonator that we made, otherwise performed in a standard pulsed ESR system. The other thing, in addition to studying new material systems, we've been using ESR tools to develop new methods to control quantum information. One of the tools which I think is, one of the technologies which I think is particularly interesting for spin ensembles is something called a microwave quantum memory. And in a sense, it's something that we do all the time. Every time you run a pulsed ESR experiment, you apply some coherent microwave pulse, and at the end you get an echo, right? It just happens to be much, much, much weaker than the first pulse that you put in. But if you change things about the way the spin and the resonator are coupled, you can bring that closer to unity, so that you put in a microwave excitation, and instead of being a kilowatt pulse from a TWT, it's a single microwave photon, but you put in that excitation into the ensemble, and then sometime later you get it out, and you get out that single microwave photon. And that's what we're trying to build when we talk about a microwave quantum memory. And you can use a spin ensemble with a strongly coupled microwave resonator. And what we wanted to do in this experiment is develop protocols for putting in not just one microwave photon, but a whole sequence of microwave photons in different coherent states, and being able to, on demand, pick out different states. So this is to develop what's known as a random access quantum memory. And the way we did this is use a chirp pulse, which will be well known to many of you. In this particular chirp pulse is known as a Vorst pulse. And one of the nice things about a Vorst pulse is that so this is sort of adiabatic fast passage type of pulse. So you sweep across some frequency. If you try and do a Hahn echo experiment with a single chirped pulse, you don't see anything. So if you look at this sequence here, pion 2 pulse or similar, this Vorst pi pulse, nothing. That's because, as kind of illustrated in this kind of diagram here, you've got the regular phasing and rephasing path from the distribution of frequencies, but when you apply this Vorst pulse, it creates a phase pattern in the spin ensemble that depends on the coupling to the resonator and the frequency, and that shifts. That provides a sort of phase shift, a kind of a wave in phase space across the spin ensembles. That means you don't see an echo. But when you apply that same Vorst pulse, and I mean the identical Vorst pulse with all the same parameters, when you apply that a second time, then you undo that sort of shift in phase space and you get an echo out. So that's sort of shown here. Pion 2 pulse, no echo, and after the second one you get an echo out. Why is this important? Well, when you have a very strongly coupled spin ensemble and a resonator, getting an echo out is losing the state that you put in. So you want to be able to refocus the spins. You want to be able to apply pipe pulses and dynamical decoupling without getting any echoes out, because then you've just lost the information. And so here's an example of two sequences. This is basically like a CP or a CPMG sequence. And in one case, we're applying always the same Vorst pulse. These are sort of AAAAA pipe pulses. And so between every second pipe pulse, you get an echo. That's what I would call like a standard CPMG sequence. The other type of sequence here we call the ABBA sequence. And here it's because your first Vorst pulse is in type A, and all the subsequent pulses have some different parameter. I can go into the details in the Q&A, but they're somehow different Vorst pulses. And so you don't see any echoes. You're refocusing the spins, you're giving them pipe pulses, but there are no echoes. And only at the end you apply a second A pulse. And then after that, you get an echo. So they're both nominally a whole sequence of pipe pulses, but one gives the echo only at the end, and one gives them throughout. And you can see that the decay time of the purple trace, where we're always getting echoes, is faster. That's because we're in this strong coupling regime. We're at the foothills of the strong coupling regime, where every echo we get is our spins leaking information or leaking energy back into the resonator, it's telling us that we're getting into this regime, and we have a method to protect the spins, even though by suppressing the echo. And you can extend this into a sort of a whole protocol for labeling different states in different ways, and then reading them out in different order. Each of these different colors is a Vorst pulse with some different chirp rate parameter. Anyway, so that's a bit about the kind of quantum technologies research and methods that we're developing using ISR. As Maxie mentioned, there's some of the reverse. So this is the vice versa part. There are sort of quantum limited amplifiers, there are superconducting microresonators, and different methods that are being developed in the context of quantum technologies that are finding ways to improve sensitivity in ESR, both in spin concentration and spin number. And Patrice Berthet's group in Saclay has been particularly driving this with the number of spins. So he, in recent work, in collaboration with us, he showed that with this micro resonator, just 100 nanometers wide, he was able to achieve sensitivities of 12 spins per root hertz. We focused on trying to sort of focus on some of the what we can learn from these experiments that can then go into instruments that translate more readily into the tools that are used in the wider field. And so made this modification with a cryo amplifier into this standard Brooker probe head. And this is a collaboration with Maxie and Gunnar and others, and shown that you can indeed achieve signal to noise improvements of approximately 10-fold by introducing this cryo amp. Basically, instead of your first amplifier in the chain being at room temperature, if you put it close to the sample and at low temperature, you can make major gains. And there's a spin-out company from a student and some postdocs that are exploiting this. So if you're interested, you might be able to get them to upgrade your probe. You can see Maxie's looking at me, so I think I need to wrap up here. Yeah, thanks very much.
Well, thank you very much to both our speakers, Sandrine and John. We've got time for a couple of quick questions before we move on to the last session. Anything from the audience? Again, if you'd like to come down to the microphone to ask your question, that would be great. No questions? Okay, I think I have a couple of questions actually for Sandrine and for John, but I think that can wait till the drinks reception later. I think we should move on in the interest of time. So yes, sorry. Oh, there's questions on there. Oh, great. Okay, sorry about that, Alberto. Go for it.
No worries. We have a question online from Richard Collins to Sandrine Heutz. What is asking in the first part of the talk, the one about pentascenes, is asking whether these systems are all just carbon-based, or is there some reason not to have some heteroatoms, as for example oxygen or sulfur?
Yeah, thanks. So they are all carbon-based. I think also just because the point is to have light elements and long lifetimes. I think that would be advantageous for if we want to use them in logic. But it is true that there are some modification of those molecules to make them more effective, maybe in solar cell for charge separation. So yeah, tuning this molecule is quite perfect in terms of the level alignment of the singlet being in resonance with two triplets, yeah, twice the triplet energy. Yeah, thanks.
And we have another one again for Sandrine's talk. This one comes from an anonymous. Can DNP NMR help in identifying quintostates?
Can what, sorry?
The question is being asked is whether DNP NMR can help in identifying quintet states.
I think so. I mean, maybe something that I didn't have time to emphasize was how excited we were about being able to identify the environment that the quintets were coming from, and so I think DNP in that sense would be able to help even more, because of course the environment in the parallel and herringbone would be slightly different with the nuclear interactions. Yeah, thanks.
Okay, thank you so much. So that brings us to our final session, which is broadly in the area of biology. And I'm very happy that Enrica will be joining us here online. So Enrica Bordignon is also on the external advisory board for PEPR and her group, and she of course has pioneered the application of spin labeling techniques combined with post-EPR to investigate proteins. And she's literally just relocated her group from the University of Bochum in Germany to Geneva in Switzerland. So I'm particularly pleased that she's able to join us online. So thank you very much, Enrica, and the floor is yours.
Thank you very much again. And actually, I would like to show you today in 10 minutes how to study proteins with EPR. And actually, your logo of PEPR fits perfectly well into what I'm going to show you. So basically, if you don't have a free radical in a protein, or if you don't have a metal active center, you have to, if you want to study by EPR, you have to spin label it. And so mostly my work is actually dedicated to proteins that do not show any EPR signal unless we introduce it. And so what we do is usually we introduce systems where we want, and we attach a label. And these labels can be gadolinium based. This is a spin 7F. Here you see. These are very nice. They are biocompatible, so you can use them in cells. I will show you later. But you can also have the normal, very common and famous nitroxide label to it. Nitroxide are smaller, but they can be used mostly in vitro, while gadolinium are bigger, but they can be working in cell. And of course, we have many others. We have copper-based, trityl-based, but today I will show you these two only. So the size for EPR does not matter. And so what I want to tell you is that because we just see the spins, we can work with very tiny proteins like 15 kilodalton proteins, but we can go up to megadalton proteins. And this is one of the recent proteins we have been working on in the lab. It's a pentameric toxin, a TCDA1 toxin, which actually is 1.4 megadalton. And we were able to label it specifically and work on it. So we can use any protein size, but what is very important is that the environment does not matter for EPR. So basically, we can work from, especially membrane proteins, which are target for drugs, one of the most abundant proteins that are target for drugs. We can really work directly in cells. I will show you later. We can do that. Or we can take it out from their natural environment and work on it in membranes or liposomes or nanodiscs or detergent. And I very much appreciate the last slide of the talk before, where this is the world of cryo-EM. So what can EPR do in this time when cryo-EM can give you all possible structures of membrane proteins? Actually, cryo-EM cannot yet do in cells. And EPR still has a high value to get conformational changes of proteins in their real environment and compare what happens in vitro versus in vivo. So what we need to do mostly is to look at proteins, and we like to see how proteins move. And so what we do, we attach maybe 2 labels to a protein, and we mostly use a tool which is called DER, double electron resonance, also known as PEPR, to measure distances between these 2 spins. And because we all know that the magnetic dipole moment of an electron spin is higher than the one of a nucleus, we can measure distances from 1.5 nanometers up to 10, 15 nanometers. So very long distances. So we have to take the proteins, label it, stick it in a tube, freeze the tube, and measure it at cryo temperature. And we can extract distances. This in EPR world is dipolar frequencies, because we know that we have, here is an example of a spectrum in gray of the gadolinium spins. What we do, if we have 2 gadolinium spins which are coupled to each other, so they are close in space, we can observe the blue spins using an echo sequence. This is a P1 pi pulse with Gaussian pulses. We create an echo, and then we can refocus the echo. And then we look at the intensity of this echo. But at a certain point, we decide to change the polarization of the coupled spins, and we do this with the red pi pulse. And this red pi pulse, we move it in this dipolar window, and we look at the echo intensity, and the echo intensity will start moving. We will see an oscillation. So basically, this sequence refocuses all the interactions except the dipolar one. So we extract the dipolar frequency out of it. And the dipolar frequency is showing here. So this is the echo intensity versus the position of the red pulse. And you clearly see here a very high frequency and here a low frequency. And because the dipolar frequency is proportional to 1 over the cubic power of R, this translates directly into high frequency, short distances, low frequencies, long distances. And we use a neural network approach to directly extract the distance information out of the primary data. So when you get the distance, when you have 2 labels in a protein and you get a distance, it could be very narrow, case 1, or monomodal, case 2. It could be bimodal, or it could have a shoulder. It could be very broad. And then it's up to you to understand what this distance means in terms of the properties of the protein. And of course, we cannot show by EPR an atomic resolution structure of a protein, but we can create distance constraints. And this helps to create coarse-grained modeling of protein. For example, case 3, you see 2 distances. This could be a protein trapped in 2 different conformations, which are in equilibrium at room temperature. Or case 5, very informative, tells you that one part of the protein is highly disordered, and then this plays in favor of a dynamic region of a protein at room temperature. So like that, if you use these tools, you can take, for example, a membrane transporter. This is a protein related to multi-drug resistance in cancer cell, and this protein expels drugs from the cell. And we want to know how to block it, how to stop it, what is the landscape. And here you see the 2 labels attached on this part can tell you in different states when the protein is open, when the protein is closed, in different conditions, for example, with ATP or ADP. This is in vitro, but I told you we like to go into physiological environment, and we can do that. So if I want to look in cell, how a protein behaves in a cell, what is the conformation, the preferred conformation, is there an equilibrium? Then I need to use gadolinium, for example. There is also tritium that can be used as labels, but gadolinium are very suitable. So what I do, I can take a protein, spin label it with gadolinium labels or biocompatible labels, and then I apply to the cells an electroporation, meaning that I apply a high voltage and the cell will become partially permeable and it will internalize the proteins from the medium. So in this case, I can internalize spin label proteins and look at them in the cytosol, in the real environment. And to be sure that the proteins are in and properly localized, I can always dope with fluorescently labeled protein, my sample, and have a look in microscopy to be sure that I've internalized them properly. And then what we can do here, and we have recently shown that we can go down to 300 nanomolar concentration of proteins in a cell, in a mammalian cell. We can extract the distances and compare them with in vitro and see whether there are differences or not. However, membrane proteins you cannot electroporate. So what do? We found a trick, which is very interesting. Let's say I want to know how these violet proteins moves in the cell. Is it open? Is it closed? This is another multi-drug resistant related transporter. So what we did, we took advantage of antibodies. I mean, in this COVID time, everybody of us know what an antibody is. So what we do, we take the protein, the violet protein, we stick it into alpacas. They will do antibodies for it. Then we take the green part, which is the part of the antibodies which actually recognizes the target. We spin label it, and then instead of looking at the protein itself, we look at the nanobodies, nanobody distances, to infer the conformation of the proteins in the cell. So this works, and actually these are data on a membrane protein on this transporter in cells, in their E. coli cells where actually they are. So this is an E. coli transporter in E. coli cells. And you can clearly see the closed and the open conformation through this nanobody trick. So I hope I could show you that EPR is not dead in this time of cryo-EM, but actually we can enlarge the scope of our research into physiological environments, and also we can correlate and corroborate data, structural data, with different techniques, of course. So now it's time for me to say goodbye and to tell you enjoy studying proteins at PEPR.
I'd like to invite Bill Rutherford to the stage. So Bill is also a co-I on PEPR. He is a world leader in photosystem 2 and photosynthesis more generally. And it's a pleasure to have you here, Bill, and I look forward to your talk.
Stand on the X. All right. So this is cut down from about an hour and a half talk. So I'm going to squeeze it in and try and get through it quite quickly. What use is EPR to a biochemist? The optional mini introduction I opted not to give, except for the one statement that EPR is that it measures essentially unpaired spins. And when I say measure that, where are those unpaired spins? The unpaired spins are in triplet states, just heard about, metals, particularly transition metals, and in free radicals. Start with the transition metals. In biology, then mainly we're talking about iron, we did manganese as well, copper, nickel, molybdenum, cobalt, others. The point is that this is where the chemical action is in enzymes. And unlike NMR, which is looking at everything, all the protons in the whole system, we are looking at where the chemistry is taking place in the heart of the active sites. When it comes to free radicals in biology, we've got all those as well. So we've got substrate radicals, we've got amino acid radicals, which are in the right in the heart of the active sites as well. Flavins and quinones, redox stuff. Tetrapyrols, that is to say hemes and chlorines and stuff. Again, these are it's where the chemical action is in many enzymes. We also have inorganic free radicals, which are relevant to biology, and the ones that I'm talking about here, you see at the top there, superoxide, hydroxyl radical, NO dot, things like that. I mean, these are evolved in essentially the redox chemistry between oxygen and water, and if you're living in a world where oxygen is present, then you'll be accidentally forming these intermediates as you go along, and that's related to oxidative stress, aging, disease, and protection mechanisms, because these work as signals as well. OH dot doesn't, because it just kills you, but superoxide and NO are both signals, as well as causing various different kinds of oxidative stress. Triplet states in biology, the main ones that I deal with all the time are in photosynthesis because they tend to be generated by light. Not all of them. Oxygen itself is a triplet state, and we could see that gets in the way in the EPR a lot. But what we look at a lot is triplet states, excited states of chlorophylls. And in fact, whenever you've got chlorophyll, light, and oxygen together, you will form the triplet state, and it will sensitize oxygen up to its first excited singlet state and kill you. And the carotenoid is in there all over the place to form its triplet state, where it dumps off the energy and saves it. saves you from being killed under those circumstances. So what information do you get out of EPR? Well, this is what you get. We'll start at the top. You get chemical identity. I mean, you can identify what's going on in there. You look at the G value. The G value is equivalent to the chemical shift in NMR, and you can do isotopic labeling, figure out what's going on. You can get concentration information from spin counting. For that, you need standards, but you don't need an extinction coefficient. So in many ways, it's easier to get concentrations out of EPR. You can do the kinetics. We've just seen kinetics before. From Anthony's talk, and you can do this, and it's limited by field modulation, but you can drop out the field modulation if you can drop out your signal to noise, or you can go to pulsed EPR, which is working in the nanosecond time scale anyway. You can work with oriented samples, so you can work on single crystals, or you can work on 1 or 2D oriented samples, and I've done a lot of that. You can look at interactions of the unpaired electron with local electric fields. That means to say that is, you can get information about the properties of the ligands, the hydrogen bonds, charges in the environment and such. And you can also get interactions of the unpaired electrons with local magnetic fields. And those local magnetic fields were coming from things like the nuclear spins, which are on the same molecule in some cases, or on neighboring species as well. This is hyperfine coupling. In addition, you can get interactions of the unpaired spin with a close by unpaired spin. And when you're dealing with these kind of interactions with local magnets, then you can essentially calculate, or you can deduce the distances and orientations of the relationships between the two spins in question. Here's just some examples of the kind of stuff that I've been doing. This is photosystem 2, but I do photosystem 1, purple bacterial reaction centers, other kinds of systems in biology, which you've got all those various bits and pieces in. But photosystem 2 is really a happy hunting ground for an EPR person, and it has dominated the field for a long time. And we got Dave Britt talking after me, perhaps, or after in a minute after that, and he was giving a talk at our place a couple of years back, and I introduced him as another main combatant in the photosystem 2 EPR wars, the 2.5 decades where system 2 was dominated by EPR. Here's photosystem 2, just to put you in the picture. What does it do? It takes light and it drives a tough reaction. That tough reaction is to oxidize water and put the electrons onto plastoquinone. It does that, splits water and releases oxygen, and the oxygen that it releases changed the planet, essentially, changed the geography, changed the biology. It allowed for respiration, made energy conversion so much more efficient that it was responsible for multicellular life developing, and it blocked out the UV by being converted by UV to ozone, and so life could come out under the stones and could become complicated. It's quite an important enzyme then. It's also quite a complicated enzyme. It's got lots of cofactors in there. But on one side it does 4-electron chemistry, which is manganese-based chemistry where water gets split, and on the other side it does 2-electron chemistry, which is quinone-based chemistry, where the quinone gets reduced. And since it's based on photochemistry and one photon gives you one charge separation, then you've got intermediate states on both sides being formed. And those intermediate states are different 1-electron state, 2-electron states, 3-electron states, and you can pick those things up using EPR. So here's photosystem 2, and we've worked on the EPR of just about every component that's involved in electron transfer in this system. And what I've done is just chosen one to emphasize the kind of things we can do. We've got a quinone here, which is the electron acceptor. We're just going to look at that. But you see right off the bat, I put the red ring around this. It's close to an ion. That is a high spin ion 2. A high spin ion 2 is a spin 2, and it is a big magnet close to our little magnet, our spin half, when we form a semi-quinone radical in this system. And what we see is that yellow line there is this complicated broad spectrum coming from a weak exchange interaction between the spin half and the big magnet of the high spin iron 2. And in fact, what we're looking at there, those wiggles in the system, reflect several different environments of this. And in fact, over the years, I've been involved in probably finding 4 different kinds of interactions. There's weak exchange couplings in there, and we can use all of those because they reflect different environments in this system. Here's what we know now about this structure, and you can see that there are 2 quinones, one on either side. The one I'm looking at in this particular instance, the first quinone QA, and the 4 imidazole ligands to the iron and the bidentate ligand from bicarbonate. That's what the BCT is. And the bicarbonate state is what changes the different forms of the EPR signal. And we know now that that's really important because it changes redox state. It's involved in bringing the protons in that are required for protonating the second quinone. And it's involved in changing the potential and protecting the system. So we're working on all of that. But in the first instance, what we were interested in doing was doing some hard spectroscopy. And if you're trying to do weakly exchange coupled systems, that's very hard spectroscopy. We worked on that a lot, but it was hard to get any hard chemical information out of it, except to use it as a probe for all this stuff. If you want to do the normal spectroscopy, you want a simpler system. The simplest system is to look just at the semiquinone. We're going to do that. We're going to change it to the low spin form by belting it with cyanide or OH minus to the system, and we can get a regular, nice quinone in our semiquinone signal. That semiquinone signal we can work on and do electron spin echo envelope modulation, pulsed EPR, and what we could see was nice modulations in the system. These come from nitrogen. We didn't expect nitrogens in those systems at all because there are no nitrogens in the quinone. There was no precedence for getting hyperfine from something else in a free radical when we discovered this. So we grew the spinach on nitrogen 15 in the greenhouse and found that it was really nitrogen 14 couplings. They all disappeared, gave us nitrogen 15 couplings. And so we knew that we were looking at nitrogen couplings through the system, and then we could do the quadrupole studies and deduce the nature of those nitrogens. So we could tell one was imidazole coupling from a histidine, which is one of the ligands to the iron, and on the other side we had amide couplings. And we could do all sorts of other things that's mentioned here. We could look at the spin densities and the pheophytin radical. We could calculate the distances between the iron and the pheophytin and stuff like that by, again, all different kinds of pulsed EPR measurements. The quinone itself has got structural information within its G values. Those G values are all hidden because it's essentially isotropic, but we can do higher resolution EPR by working at high fields, and we built an instrument. My postdoc, who was hired at Saclay, Sanan, a brilliant guy, came from MIT National Lab and built a high field EPR machine in my lab. And when we put the semiquinone radicals in there, we could see beautiful resolution. The resolution you get reflects the electrostatic environment, so you can get chemical information from that. But you can use a trick, given that all the photosystem 2s are lined up in the membrane. You can put those membranes on a piece of plastic, dry it down, cut them up into strips, put them into the magnetic field, and then rotate them relative to the magnetic field, and you can get beautiful oriented spectra. And then based on that, you can deduce the orientation of the oxygen direction and the membrane plane relative to the membrane. And that's it. And we've done the same kind of things for nearly all of those other components in the system. And I've added a few more there because we've got cytochromes and carotenoids, radicals, and God knows what. And lastly, this is the overall story on this. It just says EPR dominated photosystem 2 for years. Eventually, crystal structures came out, which then took over. And then when this crystal structure took over, thanks to computational chemistry and the structures, models were deduced on how things work. And then EPR came back in again to be able to test those models. Why? Because EPR gives information on the electronic structure of these systems, as well as that kind of structural stuff I was talking about. And electronic structure determines reactivity, and thus it remains key for actually figuring out how the chemistry works in this system. So we're into that phase in the end game of figuring out how water splitting works, and EPR is playing a major role in that. I'm just saying, so the answer to the question is, what is it good for biochemistry? A lot, more than you can imagine. And I'd like to thank Maxie for bringing in this kind of EPR to the system. In the 10 years I've been in Imperial College, I've been waiting for the opportunity to do EPR again, like we were able to do elsewhere before I came here. Now we've got it, so thank you, Maxie. And I think it opens huge amounts of possibilities for the biochemists and people interested in biological questions, which were not recognized previously. So thanks for that opportunity.
Thanks very much, Bill. So that brings us to Dave Britt, who's also joining us online. I see you are already there, Dave. Dave is also an external advisory board member of PEPR. He's also the director of the largest EPR center on the US Western Coast. He has a very long list of awards that are testimony to his ingenious use of post-EPR to studying metal-containing enzymes. So we are back to intrinsic unpaired electrons here, I think, for this talk. Perhaps also worth mentioning that while Dave is joining us from far away, but I think you've also just jumped off a boat, if I see that correctly, Dave. So I hope the sailing went well, and I look forward to your talk.
Thanks, Maxie. Can everyone hear me and see my slides? Hello? Okay. Well, I assume we're good. I just see my slides. I don't see you guys. Yeah, thanks so much for inviting me to London. It's great. I'll try to be fairly brief. You guys are getting ready for wine and beer. I'm still on my morning coffee, particularly after 4 days of sailing and all that. But we're going to talk about a little bit about iron sulfur enzymes. Again, it's nice to follow my old friend Bill Rutherford, who gave this nice overview of all sorts of different things you can do. And we're going to mostly talk about iron here and iron sulfur systems. We've been, again, doing this for quite a while. So we have a lab with 7 EPRs. Here's 6 of them, actually. So we have a mix of commercial Brookers, but also home-built instruments. So a lot of the photosystem 2 work we did back in the early days was on this home-built instrument, which was actually the second, because I had one that I built in grad school working with Mel Klein on photosystem 2. Here's our most recent. This is a quasi-optics bridge 263 gigahertz system that we put together in Davis. And our focus, you know, to contrast with the dipolar spectroscopy we just heard about from Enrica, mostly we're back into looking at hyperfine couplings. So we're mostly using techniques like indoor and eSIM and high score and ED NMR. And the whole idea is to measure essentially, as we've heard already, the NMR spectra of magnetic nuclei coupled to the electron spins. And one of the things we pushed on in iron sulfur world a lot is that this is very powerful when combined with methods like cell-free synthesis, etc., where you can introduce specific isotopes. And at this point, we can completely edit the structure of the iron sulfur hydrogenase we're looking at. So I'll show you one thing from what Bill told you about the EPR wars in photosystem 2 back in the day, even to the level of how many manganese ions are coupled into giving these EPR signals from the S2 state. Here's the sort of native state, here's the ammonia treated state. The issue is that manganese 55 is 100% abundant, and there are no alternatives you can use without becoming highly radioactive. So if you have a spin 5/2 nucleus, the number of EPR transitions goes up geometrically. So for example, if they're 4, which was highly debated, but turns out to be the case, then even if all the lines were isotropic, you've got 1,296 lines. The spectra are nicely detailed, but there are only about 19 lines, so it's very underdetermined. Whereas if you do the indoor, the number of transitions scales linearly with the number of nuclei. So here, for example, is manganese 55 indoor from this paper of Jeff Peliquin. And by simulating both the EPR and the indoor, we came up with a tetranuclear structural model that's sometimes called the Dangler model that has some reality when we see the crystal structures that came around later. So I think the way Bill talked about the phases of EPR in photosystem 2 research was typically brilliant, and how this has progressed over the years. But let me get back to this hydrogenase. So again, this is straight up in the Maxie's area of interest. We're interested in this system. It's a complex iron sulfur enzyme. It's got this crazy binuclear cluster with cyanide, CO, and this azodithylate bridge. Protons are reduced here or oxidized here on this face. There's also a 4-iron 4-sulfur cluster. And there's a lot of interest in this, in part because you can do biological H2 production. And tying it to photosynthesis, we're working now with Kevin Redding at Arizona State, who's one of a number of groups that have put some proton reducing system on the reducing side of photosystem 1. In this case, he made a chimera with a hydrogenase folded in with these Fa, Fb intrinsic centers, and you shine light on this thing and it makes hydrogen. So we're interested in this H cluster of the hydrogenase. One of the things interesting though is how's this thing made? So Bill could tell you all about photoactivation of the manganese cluster in photosystem 2, where the very electron transport system that turns over the active cluster actually can assemble it from just manganese 2 in solution, needs some calcium and assembles. This thing is much more complicated in the sense that you need enzymes to build it, to do like these organometallic bondings, etc. So that's a lot of what we've been working on in years. It turns out to make this complex iron sulfur cluster, you need 3 more iron sulfur cluster enzymes. We call these the maturases, and they're called HYDE, HYDE-F, and HYDE-G. Here's a little review I wrote when I was stuck at home 24 hours a day, if anyone's interested in the history of this and how it's been used. So if you express the gene for hydrogenase in E. coli, it will make the 4-iron 4-sulfur part. But you need the genes for these 3 maturases for E. coli to make active hydrogenase. We've been doing this a lot with this cell-free synthesis method. You can also do synthesis where you make the clusters and then link at the end. It's all been very active work. So over the time, we've built using mostly EPR, but also other isotope sensitive spectroscopies like FTIR and Mossbauer, a model for what these maturases do. So HYDE-G is one of these so-called radical SAM enzymes. It uses S-adenosylmethionine as a cofactor to make a hot radical that can extract hydrogen atoms from substrate. And the first stage of that is it actually cleaves tyrosine. And of course, we love tyrosine radicals, as Bill alluded to, from photosystem 2. So we're happy to jump in to do some more tyrosine radical chemistry. But it makes the CO and cyanide that bind to this 5th iron, which we call the dangler iron, sort of going back to PS2 times. And it makes this so-called synthon, where you have a low spin iron 2 with 2 COs, a cyanide ligand, and then the cysteine completes the coordination. This now goes to a second radical SAM enzyme called HYDE that, in our view, activates this fairly inert complex for dimerization, forming an iron 1 dimer. And then the last stage to complete this binuclear cluster is you have to complete this carbon-carbon-nitrogen part of this azodithylate bridge. And we've shown that those atoms are sourced from another amino acid, serine. Once you've made this, then it just couples to the 4-iron 4-sulfur cluster, and you've got an active hydrogenase. So by using EPR mostly, but also some other isotope synthesis, it's nice when you can do a set of isotope labelings and do EPR, mass spec, maybe Mossbauer, etc. So that's been very useful. But all the atoms of this cluster come from this high-G radical SAM created synthon, like the sulfur comes from the cysteine sulfur, the bridging sulfurs come from cysteine, except for serine is the source of the carbon-nitrogen-carbon bridge. So I thought I'd show, in limited time, I thought I'd show you how we use pulsed EPR to show that last part. We're still working on the enzymology of that. That's one of the last steps we still need to figure out. But we figured that one possibility is that there was an amino acid source for the carbon, nitrogen, carbon of that bridge. Only the sulfur comes from the cysteine that comes in the synthon. So this is one of the familiar, it's a two-dimensional envelope modulation technique called high score. And this is the background high score, you know, from various nitrogens and protons around the cluster. And if you use unlabeled amino acids, this is what you get. But now if you use labeled amino acids, using one of these cocktail kits the NMR people use, you can see a carbon 13 here that we assign to the bridge. And then you can see a nitrogen 15 that we assign to the bridge. So we're labeling all the nitrogens, all the carbons in amino acids. So this is just the start. It puts us in the hunt, but it set us up for what we call the horse race experiment, where here we know we've got observables here, these two carbon features in the high score, the two nitrogen features. So let's start the horse race between different sets of labeled amino acids. So for example, if you use these sets, and again, these are just introduced in the in vitro maturation process that builds the cluster, we can see here that proline, arginine, serine, or valine are the source of the carbon and nitrogen couplings by following these peaks. Okay, let's come around to the back end of the track. It's proline and serine, proline and serine. Now to the finish, is it proline, is it serine? Well, serine wins. So here's our serine coupling, carbon 13 couplings in the high score, and here are the nitrogen 15 couplings. To use a different method, we came back with pulsed indoor, and here we see that if we use fully labeled 3 carbon 13 labeled serine, we see a pair of carbons because we've got 2 doublets, so that the 2 carbons in the bridge are inequivalently coupled to the so-called H-ox form of the H cluster. But now we can figure out what carbon using the indoor. So if we use, instead of triply labeled C13, if we use 1 carbon, nothing, 2 carbon, nothing. If we use the 3 carbon form of serine here, we get the same thing as using fully carbon 13 labeled serine. And we can even bring the deuterons in. So for example, if you do the experiment where this 3 carbon is deuterated, here's the deuterium indoor taken at different orientation selective spots across the line. So what we have to do now is figure out the exact enzymology where hide F interacts with 2 serines, because we need 2 carbons and each serine's only supplying 1. And we think that's sort of one of the last stages of the puzzle in solving this thing. So thanks for having a look at this stuff. It is really great to have another era of pulsed EPR with PEPR in London, particularly at Imperial, where I visited a number of times, starting with the Jim Barber era, and now of course Bill's there, Maxie's there, etc. It's a great place to visit. It's also, you know, if you do magnetic resonance more broadly, you often go to, big magnetic resonance, even in biology meetings, and they're of course often dominated by the NMR folks. So it's really nice to have a place to visit, or either virtually or hopefully soon in reality, where EPR is appreciated, so you don't find yourself in this situation where people sometimes don't think about EPR so much. So you never want to be this poor fellow, and certainly at Imperial going forward, that will not happen. So that's really wonderful. Okay, thank you very much. Okay. Marvelous.
Thank you very much, Dave, and thank you very much to all the speakers in this biology session. Just before we move to the closing remarks, are there any questions from the audience? No? Do you have anything online cropping up in Alberto? No? Okay, I think perhaps given that we're already overrunning a little bit, given the technical hiccups, it's probably best if we move on. But let me thank you as well for Enrica and Dave for joining us online. That's really fantastic to have you here. Thanks again. And now I'll hand over to Oscar for the closing remarks, who is our head of department, where he has many other leading roles, of course, including being the director of the Institute for Chemical Biology with the affiliated CDT. And I think it's fair to say that, Oscar, you've done so much in getting chemistry going at this end of town, but also keeping the links to South Kensington and building up this community here at White City. So thank you very much, and the floor is yours.
Thanks, Maxie. Cheers. Afternoon, folks. So I just wanted to say a couple of closing remarks before we kind of move on to the drink session afterwards. So the first thing is to thank all the speakers today. I think did an absolutely fantastic job of kind of showcasing both the fundamental science that PEPR will unlock, but also its kind of translational potential. You've seen academics talk, you've seen people from industry, you've seen government bodies, you've seen SMEs, and I think that's one of the special things about PEPR, was when it was conceived, it was meant to cut across all those. I think Maxie's done a fantastic job of achieving that. And the biggest thanks go to Maxie. So I remember she came to me just about a year ago with a vision for what PEPR could be, and I mean, she just really ran with it. The vision became a fantastic proposal, became a fantastic interview, the facility was built, the equipment was brought in. I think she's done an absolutely sterling job, not just selling on PEPR, but also kind of running today's event. You know, I think this is the first proper lecture we've had since, I mean, the last time I was in this room, I was actually with staff voting whether to shut down the building or not because of COVID. That's how long it's been between us having an event. And whether I tell you, it's kind of really fantastic kind of being back in the community again after such a long time. So one of the nice things about PEPR is actually it's part of a journey the department's on. So about must be 7 or 8 years ago now, we all got together and had a really kind of long-term kind of consultation kind of process about where we thought chemistry was going as a discipline kind of moving forwards. And there was a realization for us that for chemistry to succeed, the challenge it would take on would require it to work with other disciplines, chemistry with engineering, chemistry with life sciences, chemistry with materials, that chemists could make a big impact, but they weren't going to work on their own. And I think that was completely at odds with the infrastructure we had at South Ken. At the same time, we had strong demand from industry, SMEs, and large corporate partners to co-locate us at scale. We couldn't do that at South Ken. And we really realised we wanted to interface on a different kind of length scale with other kind of disciplines. And as we were having these conversations, it was a serendipitous kind of moment in history that college got hold of the White City campus. Now that's what it will look like in about 10 years' time, okay? So we're on the far right corner, but already, you know, circa something like about £1 billion investments already gone to the campus, okay? When we came here, there was nothing here at the time, but the vision that we had of co-location of entrepreneurship, industry, academia, were exactly the same as White City was. And that's what seemed a really kind of good move to undertake at the time. And I think when we did that, something like PEPR was exactly what we dreamed of. A facility that wasn't just for academics and large corporate partners. And if you look at universities, we tend to run facilities that look after academics. That's really important. They tend to engage with large corporate partners, probably second in the line. Then thirdly, are probably SMEs from within it that come out of our own ecosystem, but last in the queue tend to be SMEs that we necessarily have not grown ourselves for a variety of reasons, from, you know, paperwork, administration, kind of bandwidth issues. But here in White City, you know, you've heard today from people like Polymaterial and similar companies, this is a completely different landscape to us. At South Ken, we're surrounded by museums and fantastic kind of, you know, cultural kind of venues. What we're surrounded by here is a really bubbling ecosystem of SMEs, and many of them have not come from Imperial's kind of portfolio. And we're trying really hard as a department to work with them. That's exactly the things that PEPR committed to doing, is working with academics, but also SMEs, be they our own or external ones. I'm kind of really looking forward to that kind of growing with time. To do that, you need a facility. This is what the MSIH is. So if you've not done the tour online of PEPR, please, I'd encourage you to do so. But the whole department is structured around this idea of kind of co-located kind of clusters. South Ken was, if you went to our old building, it was literally designed to prevent collaboration. If you said to someone, build a building that isolated people, it was a South Ken building. It was a set of rabbit warrens. You could hide your own research group and not see a colleague for like 20, 30 years. You weren't sure if they were in the department or not. Here, everything's open plan. The clusters are kind of shared, and it really adds a lot of value. And PEPR's kind of really bought into that kind of ethos, and it's really exciting to see. Similarly, as I mentioned already, the ecosystem, you've got scale space, you've got open cell, you've got White City Place across the road, literally within about a 10-minute walk of this building, you have hundreds, not tens, hundreds of SMEs on our doorstep. You know, as a university, you could not dream of having that kind of business nearby, but we need ways of engaging with that in PEPR, as our facilities like RAW and the Agilent suite are kind of key to making that happen, kind of moving forwards. You need talent people to use these facilities. So in the department, there's about 800 people at steady state. The UN's kind of filling up similar numbers of people. You've got the iHub next door. You've got the Hammersmith Medical Complex across the road, about 3,000 clinicians there. And that's something that PEPR will benefit from. It's not just helping people across the UK, but a really kind of strong talent base here nearby at the campus. And also, I think one of the special things about PEPR is it will actually develop its own instrumentation. And to do that, it needs prototyping facilities. And here at White City, we've got the advanced hack space. We kind of make that kind of happen. So back to the beginning, you know, we started a journey a couple of years ago. We'd hope we get to places like this. We'd hope we'd have facilities like PEPR running. And I just wanted to give my congratulations, Maxie, on an absolutely fantastic job of getting PEPR up and running. And we look forward to kind of working with you over the coming years. Thank you very much, folks.
So much. I just want to finish by thanking you for being here, those in person and also the online audience. It's really great to have both, and it worked out with this hybrid event. And thank you especially to our online speakers, of course. I hope you enjoyed the talks. And with that, I think the floor is open for the reception upstairs. Also some pizza in case you're hungry. And apologize to those of you joining us online that you can't join us for this part, but hopefully there will be an opportunity to catch up in person soon. And especially for the external advisory board members who aren't here in person today, hopefully next time round you will be having a chance to see it all in person. Thank you so much.